Okay guys, so I've given you a couple minutes to be able to figure this out. So essentially what you do here is, remember how I said it's the atomic weight equals protons plus neutrons. So essentially what you can do is 12 equals 6 plus n. If you remember your math, you subtract 6 from both sides, and then you have neutrons equal 6. So that essentially can tell you how many neutrons you have. Now, the one thing that we have, so we have protons, we have neutrons. What about the electrons? Do you have any idea? Well, remember how I said all these are neutral? And protons, P for positive. Electrons are negative. Well, if they're neutral, it means that you have to have the same number of protons as you do electrons. So essentially, it would be 6. And if this tells you why chemistry is evil, I can't tell you any other reason that would make it more obvious than this. Okay, so those are protons. Now, I told you a few minutes ago that to get the atomic weight, you averaged all the different isotopes of carbon together. Well, this is what an isotope is. It's multiple forms of an element, and it differs in its neutrons, right? So essentially here is carbon-12. That's the normal, everyday average carbon. As you can see, there's 6 protons, 6 neutrons, and 6 electrons. Well, as I mentioned earlier, carbon is always 6. It never changes. So essentially, the proton number for carbon-13 would be 6. So would carbon-14. Now, because we have essentially the number of positive charges and negative charges remain the same, that's the reason why every single one of these has 6 electrons. What changes is the neutrons. This is giving you the mass. So carbon-12 is the mass. The 13 is the mass. The 14 is the mass. So essentially what you do is you take your mass, you subtract it from the number of protons, and that gives you the neutrons, right? So this guy, normal, we're good. But if you look at here, whoa, right? He's at 7. So carbon-13 has plus 1 neutron. Oops. So how many more neutrons do you think 14 has? Yep, 8. And you can tell this by, if you were to look at an atom like we were looking at earlier, and you look at the nucleus, right? You count and see how many protons you have. Then you look at your periodic table. First one, you look at the number of protons. Second, you look at your periodic table and figure out how many neutrons you have. And then you can look and count your neutrons. And that'll tell you if you have an isotope or not, if it's off what it should be. Now, isotopes are really, really important in science because we use them a lot of times, not just for research. I used a few different isotopes when I was in grad school, but your physician will use them. For instance, you can use isotopes, and isotopes are essentially radioactive, right? And they're radioactive essentially because having the additional neutrons makes it unstable. So essentially, it's slowly releasing energy until it can go back down to the number of neutrons that are normal. And so essentially, we use this. We have radioactive iodine. that we use. This is one of the first and most common that was used initially. And iodine is used in for your thyroid to work properly. So essentially, they would have people drink radioactive radioactive iodine. The iodine would be targeted to the thyroid, and then they could go and actually do an MRI and look and essentially do a scan to locate the radioactive material which was siphoned into the thyroid. Sorry, it's kind of late tonight, so I'm getting a little tongue-tied here. Another one that they've used is essentially radioactive glucose. This one is super cool because essentially they found out that cancer cells use glucose at a higher rate than regular cells. It's called the Warburg effect. So essentially what you can do is a patient can drink radioactive glucose. Cells that bring it into them faster take it up, and then they can do a scan and then look at the areas of your body that take it up faster than others. Now things like the brain, they know it takes up a lot of glucose. So if you saw that area light up, you wouldn't think anything of it. But if you see certain spots that aren't supposed to light up at all, and they are, that is an area that potentially can be carcinogenic, and then later they can go in and do a biopsy and do something that is a little bit more of a surgery versus something like this where you can go in and not have any surgery at all. So that's how, basically, that's why protons and neutrons are important. But what we're going to focus on the majority of the year are things like chemical reactions and bonds and how DNA is put together and, how do we break down food? Well, all of that is determined by chemical properties. And the chemical properties in an atom, does anybody know what it's determined by? Come on, you guys know this. What's the only subatomic particle we have not talked about yet? Electrons. And they are located in areas called orbitals. And that's what we are going to talk about next. So I'm going to go ahead and pause here and let you take a break, and we will start with the next video.